our group is presenting our project on food traffic versus work, retail forecasting 2.0. And for this project, we used a combination of machine learning and deep learning model to predict hourly customer traffic for multiple companies. And we selected this project for the Kaggle competition. From the Kaggle competition, and our group officially signed up and participated in the competition using the real data set provided on this platform. And this competition mainly focused on forecasting hourly foot traffic of for like several retail business, and this made a great opportunity for us to apply like time series forecasting techniques in real world competitive settings. Okay, so moving to the slide number 2, here is the roadmap for today's presentation. That's introduction, why forecasting customer traffic matters, and then the data set, like what kind of data that we used and how we prepare it, and then the methods. Simply that's the feature engineering, pre-processing, and the model development. And then we will move to the result, that's like performance of all the models, and then discussion and the conclusion. So by the end of the presentation, you will clearly understand like how we build these models and why certain model perform the best. So on slide number 3, we discuss that we work with the multivariate like time series data set containing like approx like 50k rows of hourly customer traffic records. And here our main objective is to predict the hourly customer traffic for multiple companies, like I said before. So all the customer values are normalized between the 0 and the 1, like means which helps the model to learn the model learn across the different business with the accurate prediction, and business can improve staffing schedule and also prevent the overstaffing or like understaffing, and manage the inventory more effectively. And also it reduces the operational cost. And yeah, we explore like both the machine learning and the deep learning models. So moving to the slide number 4 here, our data set forms the foundation of the entire forecasting project. So here each row represent 1 hour of activity for a specific company. Here you can see the data set include 5 key models, that is company, category, data, date and hour, and target value. Company identifies which business the record belongs to. Category is, in our case, like every records fall under the same category, that is customer. This means the target variable always represent the number of the customer during the hour. And date and hour, these two fields gives the exact timestamp of like each observation. And the target value is the normalized customer count, the original value having a scale between the 0 and 1, which helps ensure the consistent training across the different companies, especially because like one company may naturally have more customer than others. So here you can see that the more important advantage of the data set is like it has no missing value. And this means like we didn't have to perform like heavy data cleaning or anything, which often complicates the forecasting task. So moving to the next slide from here, I think the Hemant will present it.
Okay, so okay, so I'm going to talk a little bit about the problem statement, well, problem or the motivation. And our data set basically requires reliable traffic predictions to match workers to demand. Having these time-varied series data set really helps navigate or understand the customer's inflow or, the peak traffic during specific time, which in return helps make accurate predictions to minimize overstaffing or understaffing requirements. The goal of this competition or the project in itself is to kind of find the best model that will accurately predict specific forecasts of customer inquiries or customers arrivals within specific organization stores, and can help mitigate these issues with overstaffing or understaffing. That's pretty much our motivation. I'm going to move to another slide. This part's important because we did a lot of pre-processing. We did a lot of prerequisites before we moved to actual implementation of the different models that we used. So our data set contained categorical variables such as company and category. These are text labels, and models like Random Forest, XGBoost, MLP, and even convolutional neural networks cannot learn from raw text. So they need to be converted to something that these models can ingest and perform, learn patterns from numerical input. So we converted these text labels into numerical codes using label encoding. This step allowed the models to distinguish between different companies, categories, and to learn relationships, such as which companies tend to have higher or more variable customer traffic. Without this encoding, the model would treat these columns as non-usable data. So this was a very important part. We also did some time-based train validation split. Because this project is a time series forecasting task, we cannot randomly split the data like we do in traditional machine learning algorithms, where we used to do, like, for example, when we did the first assignment, we did 80-20 split, 70-30 split. In this case, since this is a time varied, random splitting mixes past and future events together. So this causes something called data leakage, where a model accidentally trains on future information. That would make the model unrealistically good during training, but completely unreliable in real-world forecasting. To kind of avoid this, we used a time-based split. So the earliest 50,000 rows were considered to be the training data, and then we used the most recent 500 data that wasn't used for training purposes at all to verify the accuracy of the model's predicting capabilities. That's pretty much what we did for the pre-processing part when it comes to the splits. For adding date time features, we did a couple of things there, like machine learning models do not have any built-in awareness of time, so they will not have an understanding of, when was the last Monday, a weekend, 9 a.m., unless we explicitly tell them. So that's where we engineered several calendar features like day of the week, weekend indicator, month and hours of the day, which these features allow models to learn real human behavioral cycles, the time cycles, such as when is the weekends or weekdays, how is the pattern trends during seasons or rush hours, things like that. So by giving the models these time-based cues, we teach them how customer traffic rises and falls throughout the week and across the day. And then we move on to a little bit of lag features. This is just splitting the data, or categorically organizing the data to specific portions, like the last 24 hours or the last 48 hours or last week. So we did it in three different lag features, which was the last 1 day, last couple of days, and the last 1 week. Which gives the model, especially models like decision tree models, have navigate through different time variations and be able to predict future based on past. So these models somewhat form a memory with the use of lag features. At the end, we use some PCA components. PCA is, I would say it's a method, dimensionality reduction method that we have incorporated here. Principal component analysis in plain words is just summarizing everything, summarizing most of the things of the underlying data set and provide a data in a simpler, cleaner format that it's easier to immediately ingest for the models. So this helps models like multi-layer perceptron, helps random forest and XGBoost by giving them like distilled information rather than forcing them to parse through the noisy individual features. The next slide is related to the models used. These are the models that we've used. XGBoost and random forest were the ideal data sets for and non-linear patterns. We used multi-layer perceptron. We used convolutional neural network, and we also used long short-term model. And they were trained using the Atom Optimizer, adjusted for the best validation loss. I'm gonna give the next slide to Anupam to continue with the rest.
So here we have got three of the architectures detail, three of the models that we have used. So the first one is the MLP. So here in our project, like MLP achieves the best performance among all models. So it is designed for like clean structure inputs, and our feature aligns perfect with its strength. And the second of the model is like CNN. So these filters are excellent at detecting like the repeated patterns and local trend, which makes suitable for like 24-hour foot traffic cycle. But there is one main problem of CNN. It only focus on like the short-term windows, so they do not fully capture longer weekly or monthly trends on its own. And we have got a lot of like the month, date, time, so it doesn't capture that. And the one we use is like LSTM, which is good for like the bigger ones, but in our data set the sequence were like relatively like short and not strongly periodic, so the LSTM did not receive enough consistent patterns to learn deeply. Next one. So here is the result that we have obtained. So here we can see like MLP has the best RMSE. So how we detect its best, because its RMSE and YME is like lower in comparison to others. And followed by the MLP, we have got the XGBoost and random forest. One more thing, like to detect which it predict more, we have to look at the R2 score as well. So in which like if the prediction is like closer to 1, then it's like highly predicted. So MLP, the R2 score of MLP was the highest, and the MLP R2 score and the RMSE and MAE score were higher in LSTM and CNN, so they were kind of lagging behind. Here we can see the result between the XGBoost and the random forest. So the red line represent perfect prediction. If all the points set exactly on that line, the model would be perfect. In both XGBoost and random forest, dots are like closer to the line, and the clustering is tight. And there were like very few dots that were like going out of the box. So here we can see the comparison, like MLP, all the dots are like closer to the red line, like it means it is like highly predicted. But if we look at the LSTM and CNN, the dots are like way too far from the actual predicted line. So they were like not much effective for the prediction. Yep. The next one.
Okay, so I'm focused on the comparative performance for of our mode. Overall, we rank the mode from the best to the worst. It's followed with MLP, SG Boost, Random Forest, LSTM, and CNN. So for the in the traditional machine learning mode and the simple neural network clear outperformed the more advanced sequence mode. And the main reason is the top three traditional machine learning mode were able to fully use our engine features, especially the lags features and the calendar information. Because the MLP, XGBoost, and the random forest were treated on rich tabular data and include the company identifier and day of week, hour of day, and key lag volume, like the volume from the same hour yesterday or last week. They had a much stronger signal to learn from. In contrast, the deep sequence model only saw the short row sequence of the post volume with very limited context. And for the comparative result, we make this comparison more concrete. Use RMSE or the root mean square error, which means how far our prediction from the true volume, and the lower is the best. So for the top picture, it showed the random forest, XGBoost, and the MLP. All three are the tight range around 0.07 to 0.08, which is the stronger performance level for this normalized data set. And for the neural network mode, their error are closer to the 0.10, which is noticeably higher. This escape may not look huge at the first glance, but in forecasting, the constant difference of the size means many more hours where the prediction are off by the meaningful amount. For the error pattern, in general, the most points lie close to the diagram line, which means predicted volume match actual volume quite well. However, we do that the largest error happen during the unusual spikes or the sudden drops in customer traffic. That, for example, like the specific event promotions and at a normal quiet period. And for on the discussion slides, the biggest takeaway from our project is that the feature engines was more important than the model complexity. The lag features, especially the lag 168, with correspond to the volume and volume from the same hour in the period provide week turn out to be extremely powerful. They discussed Disney encode weekly the seasonal lighting. And for next.
Now let me explain how our model behaves. So the NMLP worked the best because the feature we created already captured the important pattern in the customer traffic. This means that the model does not have to guess the pattern. The clue were already given to it. So these features include hours of day, day of week, and a lag value like the same hour yesterday or the same hour last week. So the deep learning model LC, TM, and CNN do not perform as well. So they only got the raw sequence data and did not get the extra information like the weekday or a company. So this made it hard for them to learn the seasonality or the business specific pattern. Also, deep learning usually requires a much bigger data set to learn long-term pattern. With our data set side, the deep learning model struggled and the mostly predicted value covered the average. So overall, the simpler machine learning model did better because they used the engineered feature effectively, while the deep model did more data and more content. Next slide, please. So our project has a few limitations. The first limitation is that we did include outside factors such as weather, holidays, or a special event. These things can strongly affect the customer traffic. For example, weekend, snow days, or a celebration or a festival can cause big changes, and the model could not account for those because the data did not include them. The second limitation is that the deep learning model only use the traffic sequence itself. They do not get the access to the additional features like the hour, weekday, or the category, which hurts their performance. And the third limitation is that our model, especially the deep one, needs stronger structure to capture the weekly pattern. Weekly seasonality was the major part of this data set, and without the right model design, it becomes harder to learn consistency. So the next slide. For future improvement, we can do several things. several things. First, we can add external features like holiday, weather condition, or a local event. This factor can provide more consistent content and can help the model understand why traffic suddenly increases or decreases on certain days. Secondly, we can try hybrid model, for example, combining LSTM and XGBoost may give us the sequence understanding of deep learning and the strong feature handling of the machine learning. Third, we can explore attention-based model or a attention-based model. This model are good at learning long-term patterns in the time series data. Next slide, please. So to conclude, the machine learning models like MLP, XGBoost, and Random Forest gave the best result. The deeper learning model did not perform well because they do not have enough feature or enough data to learn the pattern. Overall, the key to our success was feature engineering, not the model complexity. So this shows that the structured time series data, simpler model with good features can outperform deep learning, and with more external feature, even higher accuracy can be achieved. So this is all for our presentation. Thank you so much.